third and final day talking about cryptography. We're going to do a little bit more with modular arithmetic, which is what we started talking about last class, using remainders as part of the encoding process. So the modular arithmetic ciphers that we have seen used addition and subtraction, right? We started out with the Caesar cipher where you just add 3 to every letter. Then we added a keyword over and over. And then we used the keyword plus the message itself as our encoding key. So but we were always adding. We were adding to encode, subtracting to decode. But you could also multiply or do some combination of multiplication and addition. So a multiplicative cipher is one where you just multiply, and an affine cipher is where you multiply by a constant number and then add another number, possibly different. So, for example, we'll encode the message attack at daybreak using an affine cipher where you multiply by 3 and then add 5. So I'm going to do it out one step at a time. We'll start by multiplying each of these numbers by 3. So 0 times 3 is 0. 19 times 3, I might need a calculator. 57, okay. 57, 57. 0 times 3 is 0. 2 times 3 is 6. 10 times 3 is 30. 0, 57. 3 times 3 is 9. 24 times 3, 72. 1 times 3 is 3. 17 times 3, 51. 4 times 3 is 12. 0, 10 times 3 is 30. Okay, so I've done multiplication by 3. And it does help to keep yourself organized if you kind of make a little grid. So I think I'll do that. Or if you use graph paper, so it's already gridded for you. Okay, so next, now I've multiplied by 3. The next step is to add 5. Okay, according to this cipher, multiply by 3, then add 5. So I'm going to get 5, 62, 62, 5, 11, 35, 5. So just adding 5 to every number that I got in the previous step. 57 plus 5 is 62. 9 plus 5 is 14. 0 and 5 is 5. 72 plus 5 is 77. 8, 56, 17, 5, 35. Okay, now, any numbers that are too big, right, that are not between 0 and 25, because 0 to 25 represents my letters, right? Anything that's too big, last class, what did we do to the numbers that were too big? You minus 26, but what if it's still too big? Like 62 minus 26 is still going to be too big. Do it again. Yeah. Or you could think of it as dividing by 26 and giving the remainder. Because repeated subtraction is the same thing as division. So you can subtract 26 over and over until your number is the right size. Or you can divide by 26 and give the remainder. It's really the same thing. So 5 is already between 0 and 25. 62, I could just subtract 26 over and over because it's going to represent the same letter because there are 26 letters of the alphabet. So 62 is the same as the number 10. 5 is already small enough. 11 is already small enough. 35 minus 26 would be 9. 5 is good. 62 we already determined was 10. 14's fine. 5 is fine. 77. 25. So we do 77. We subtract 26. Still too big. Minus 26. We get 25. I subtracted 26 as many times as I needed to till my number comes out between 0 and 25. 8 is already between 0 and 25, so I'm good there. 56 is too big, so I subtract 26. And I get 30, which is still too big, so I subtract 26 again, and I get 4. 17 is already small enough, it's between 0 and 25, so it stays 17. 5 is already small enough, and 35 minus 26 is 9. Finally, the last thing I do is change these back to letters. So it's handy to have the alphabet written out with letters next to it. Yep. Okay, so 5, A is 0, so we go B, C, D, E, F is the letter 5, number 5. What's 10? K. And 5 is F. 11, 9, J, F. 14, thank you. Z, I, E, there we go. So there's our message. Turned into what looks like garbage, right? That is attack at daybreak encoded using an affine cipher. But before we talk about how to encode, I'm going to have you do one for practice. I mean, how to decode. You're going to practice in. Okay. So now that we know how to encode the message, we have to figure out how to decode. Okay. So for our encoding process, we multiplied by 3, then added 5. So to undo it, you have to undo it in the reverse process that you did it. Kind of like if you put on your socks and then put on your shoes, to undo it, you have to take off your shoes, then take off your socks, right? Undo it in the reverse process that you did it. So if you multiply by 3, then add 5, the first thing you would do is subtract 5. Then what? Well, yeah, it would normally be divide by 3, but how do you divide 5 by 3 in modular arithmetic without giving a remainder? It's kind of weird. So we would, to get from T to encode as K, we multiplied by 3, right? We got 19 times 3 was 57. It's 57. And then if you take that mod 26, you do minus 26, minus 26, and you get 5. That's why that got encoded to F. And then you add 5 and you get 10. So to go backwards, we need to subtract 5. And the next step we would naturally think would be to divide by 3. But it's actually not possible. Division isn't possible in modular arithmetic. In this new world we live in where all we care about is remainders. So there is a way to undo multiply by 3, and it turns out that what you need to do to undo multiplication by 3 is to multiply by 9. And I know it sounds really weird. It does have to do with subtracting 26. So if you multiply by 9, let's see what happens to A when you multiply by 3 and then by 9. If you multiply 0 by 3, you get 0. And if you multiply 0 by 9, you get 0. So A goes back to A. But let's not look at this table yet. Let's look at B. Right? If we multiply by 3, so B is the number 1 in the alphabet. Multiply it by 3, you get 3. Multiply that by 9, and you get 27. And 27 is the same as what letter of the alphabet? 1, right? It's the same as the number 1 because when you subtract 26, you get 1, which is the letter B, right? So here's my B gets encoded as 3, right? So this is my encoding by multiplying by 3. Then my decoding is multiplying by 9, and that just brings me back to B. Yeah, let's see if it works for a couple of other letters. If I do, say, F. What's F as a number? 5. So if I multiply 5 by 3, I get 15. Then multiply 15 by 9. 135. And then I have to take that mod 26, right? Subtract 26 over and over again. Minus 26, still too big. Minus 26. Minus 20. Till you get below 25. 5. Which is back to F. Yeah. So multiplying by 3 and then multiplying by 9 always brings you back to where you started. That gives you the round trip. Okay, it encodes as one letter and then decodes back to F. What?
Do we have to do the round trip?
If you want to decode,
always goes back to the same letter.
well, the idea is if you want to decode, then you have to figure out how to make the round trip. Yeah, you got to subtract 5 first. Yeah. Yeah. So why does it work? Why does multiplying by 3 and then by 9 always get us back to where we started? They're inverses. I heard that. That's great. So they're inverses because when you multiply by 3 and then by 9, you're really multiplying by 27, right? Because 3 times 9 is 27. And in modular arithmetic, in the alphabet, right, 27 is the same as 1. Because when you subtract 26, you get 1. So multiplying by 3 and then by 9 is like multiplying by 1, which doesn't change the letter. Does that make sense? Brings you back to where you started. So we say 9 and 3 are multiplicative inverses in mod 26. And we can also say multiplying by 3 and multiplying by 9 are inverse operations. Figuring out the inverse operation using multiplication is the key to encoding and decoding. So I just came up with that 9 out of thin air, right? I just said multiplying by 9 is how you undo multiplying by 3. So the way you figure it out is first you have to know that it's reversible. First you have to know that there is a number that you can multiply by that will get you back to where you started. So let's see what happens if we do multiplication by 6. If we take each letter of the alphabet and multiply by 6, it turns out that B and O will both be encoded as G. Okay. Which means that if our message that we receive that's encoded that looks like a bunch of garbage, we won't know if G should get decoded back to B or back to O. So multiplication by 6 is actually not a reversible encoding method. So you wouldn't use that one because you can't figure out how to decode it. Okay. Can't use this one because it's not reversible. And the problem's even worse if you try multiplication by 13. If you multiply every letter of the alphabet by 13, every letter will get encoded as either A or N. So your whole message will just be A's and N's, and there'll be no way to figure out how to get back, how to decode it. So how do we know in advance whether a particular multiplication operation is reversible? So it turns out that if you multiply by a number that shares a factor with the modulus, then it will not be reversible. So remember, the modulus for us is 26, right? The number that you divide by. So 6 and 26, 6 was not reversible because they share a factor of 2. 2 goes into both of them. And 13 is not reversible because 13 and 26 share a factor of 13. The 3 was reversible because 3 and 26 have no common factors. There's no number that goes into 3 and into 26 other than 1.
So
7 would work, yep. 5 would work, yeah. Well, 13 didn't work either, so it's not just... And 6 didn't work, so that's an even that doesn't work. Yes? Fantastic observation. So people were calling out numbers that would work. They were saying 5 and 7 would work. Those would work because they're, well, not necessarily because they're primes. They're primes that don't go into the modulus. You just said if the modulus was prime, you could use any number because there's no way they'd share factors. So for this reason, we often change the modulus from 26 to a prime number. Okay, so a prime number, remember, has only divisors of 1 in itself. So 27 is not prime because 3 goes into it and 9 goes into it. But 29 is a prime number. And it's relatively close to 26, so we would not be changing too much by using 29 as our modulus instead of 26. So the advantage of using the prime number is we don't have to worry about the number we multiply by. We will always find a reversible. The disadvantage is that our modulus is now bigger than 26. So let's encode retreat at once using multiplication by 6. And then we're going to do mod 29 instead of mod 26. So I'm just going to take each of these and multiply them by 6, and take the result mod 29. That's a great, it has to be below 28. Yes, it has to be below 28. Okay, so 17 times 6. 102. Oops. Really? I must have messed up. 102. 4 times 6 is 24. 19 times 6. 17 times 6, 102. 4 times 6, 24. 0 times 6 is 0. 114, 0, 114. 14 times 6, 84. 13 times 6, 78. 2 times 6 is 12, and 4 times 6 is 24. Okay, so I multiplied by 6. That's the only step here. All they're saying is multiply by 6. There's no adding step. And now we just take the result mod 29, which means subtract 29 over and over till you get a remainder, till you get a number that's between 0 and 28. So you can't subtract 29 anymore. Okay, so 102. 102 minus 29. 29 minus 29. Okay, so 102 minus 29, right? Because we do 29 because when we were using 26, we subtracted 26 over and over till we got a number from 0 to 25. Now we subtract 29 over and over till we get a number between 0 and 28. And we get 15. 24 is already the right size. It's already small enough. 27, great. And we know 102 goes to 15. 24 is small enough. 0 is small enough. 114 goes to 27. 0 stays. 27. Anybody have 84? 26? Okay. 78? 20. 12 is small enough and 24 is small enough. Now, the problem with changing this back to letters is that I have some 27s in there. And 27 does not correspond to any letter of the alphabet. Neither does 26. Nope. What we're going to do is even simpler than that. we are not going to change it back to letters. This is going to be the code that we send. We're going to send a list of numbers instead of letters.
So if anything's over than 26.
Yep, we just leave it as numbers. Well, you could do that. Yep, you could do that. You could assign some symbol to 26, 27, and 28. No, the standard practice with this one is to send numbers instead of letters. This is called a multiplicative cipher. If you do multiplying and addition, it's called an affine cipher. Yes?
Would it be easier to simply replace the output of 3 letters with X, J, and W, Q, and then going down,
Sure. Yeah, you could do that. That's a good idea. Yeah. So if you took 3 uncommon letters out of the alphabet and just trade them, say take out X, J, and Z, right? And make them always come out as some other letter, I don't know. Then yeah, you could use 23 as your modulus, and then you wouldn't have leftovers. Okay, so yeah, we get numbers like 26 and 27, which we cannot turn back into letters. So when we use multiplicative and affine ciphers, if we use a modulus bigger than 26, we simply leave our encoded message as a sequence of numbers, and you send a sequence of numbers instead of a sequence of letters. Okay, so before we go into how to decode, now I'm going to give you one to practice. So it looks like everybody seems pretty comfortable encoding, right? Follow the directions, multiply by 4, add 3, take the result mod 29, and you do not turn it into letters at the end, right? Okay, so now we're going to talk about how to decode. So let's say we want to decode a message that was encoded using multiplication by 6, and the result was taken mod 29. Okay. If you're not done with that homework example, just please put it aside for now so that you can learn how to decode and you can finish it later. Okay, so we encoded by doing times 6, then mod 29. So in order to decode, I have to undo multiplication by 6. So remember we said, can you guys stop talking about that problem? You're distracting me. Thank you. So remember we said that normally to undo multiplication by 6, you would divide by 6, but that doesn't work in modular arithmetic. So what we need to find is another number to multiply by that undoes multiplication by 6. So we did an example earlier where 3 and multiplying by 3 and multiplying by 9 were inverses in mod 26. So I need to find a multiplicative inverse of 6 when I'm working in mod 29. So the way we do it is we say, well, I want to do 6 times something else that will get me back to 1, right? So because that way, when I multiply by 6, then by the inverse of 6, it'll be like I didn't multiply by anything at all, and it will give me the round trip. It'll give me back my original letter. So is there a number I can multiply 6 by, a whole number between 0 and 28, those are the only numbers that exist in mod 29, that will give me 1? Why 5? Aha, yes. Yeah, that's a good way to think of it. Another way would be, well, there isn't really one, but there is one that would give me 30, right? Because I'm working in mod 29, I can always add 29 to any number, and it's the same number, right? Because it loops. So is there a number I can multiply 6 by to make 30? 5. So 5 is my multiplicative inverse of 6 in mod 29. Because 6 times 5, 6 and 5 are always going to be inverses in mod 29. Yeah.
So does that also apply to like whatever is?
No, it remember 6 didn't have an inverse in mod 26.
I mean, like
Yes. Yeah, let's do another example. So let's say, pick a prime number, let's say 31, mod 31. Let's find the multiplicative inverse of 7 in mod 31 arithmetic. Okay, so I'm looking for 7 times something that will give me 1, right? What number is equivalent to 1 in mod 31? 32. And I can keep adding 31 and get numbers that are equivalent to 1. 31 plus 32 is 63. 63 times 31 would be 94. 7 times what would give me 63? 9, all right. 7 times 9 is 63. So 7 and 9 would be inverses in mod 31. 31 twice, and you'd get 1. Yep. So I was coming up with numbers. Let me answer, please. I was coming up with numbers that are equivalent to 1 in mod 31 arithmetic. So, okay, so here's what mod 31 arithmetic looks like. I start with 0. 1, 2, 3, 4, 30. And there is no 31, right? Because I have already written down 31 numbers, 0 through 30. So 31 is back here. 32, 33, 34, 35. This number would be 61, right? And then 62 is back here. 63 is equivalent to the number 1. So mod 31 arithmetic, is just a loop. Modular arithmetic is just a loop. So let's do a smaller one, like mod 5 arithmetic. Right? Will be 0, 1, 2, 3, and 4. Because those are the only remainders you can get if you divide a number by 5. 0 through 4. So the number 5 is actually equivalent to the number 0. Because if you divide 5 by 5, the remainder is 0. 6 is equivalent to the number 1. So all these numbers, I can generate a list of numbers that are equivalent to 1 in mod 5 arithmetic. Yeah. Yep. Yep. So all of our moduluses thus far have been like 12 for the months, 7 for the days of the week, 26 for the letters of the alphabet. But you can do it without having anything that corresponds to it, just numbers. Take one of each of those, the slides and the homework. And that one single sheet there. All right, so let's do one more. I want you to find multiplicative inverse of 3 in mod 5 arithmetic.
So is there like a specific way that you can lay it out?
I just do 3 times something equals 1. And then I write a list of things that are equivalent to 1. So to generate a number that's equivalent to 1 in mod 5, you can just add 5 over and over. So I would have 6, 11, 16, but I can stop at 6, right? Because now there is a number I can multiply 3 by to get 6. So 2 would be my answer. Yep. Yep.
Does it matter how long it takes you to
Nope.
get something that?
Nope. You just do it until you can get something. Yep. Uh-huh. Yeah. Yeah, they're just going up by 5s. Yes, exactly. Not to have 1, not because these are all numbers that when you divide by 5, you get a remainder of 1.
But you're not finding a factor.
No, all you care about is the remainder. Yeah. Yeah. Okay, so remember we are looking at mod 29. So we wanted to find the multiplicative inverse of 6 because we multiplied by 6 to encode in mod 29. So this is the first example we did. Let's just do it again now that we've done a few. Okay. Multiplicative inverse of 6 in mod 29. So I'm looking for 6 times what will give me 1. Well, there is no number that I can no whole number I can multiply 6 by to get 1. So I'm going to generate a list of numbers that are equivalent to 1 in mod 29. No. So I need numbers that are equivalent to 1 in mod 29. That is numbers that when I divide them by 29, I get a remainder of 1. So what's the next number bigger than 1 that when I divide it by 29, I'll have a remainder of 1? 30. And an easy way to get that is to just take the 1 and add the modulus of 29. 1 plus 29 is 30. 30 plus 29 is 59. 59 plus 29. Yeah. So these are just a bunch of numbers that are equivalent to 1 in mod 29 arithmetic. Any of these numbers, if I divide them by 29, I get a remainder of 1. That's what it means to be equivalent to 1. Now, I go back to the left side of my equation and I say, is there a number I can multiply 6 by to make 30? 5, yeah. So 5 is my multiplicative inverse. 5. Okay, so now I'm going to use that multiplicative inverse to decode this message. Okay, it was encoded by multiplying by 6 and taking the result mod 29. So to decode, I'm going to multiply by 5. Multiply by 5 to decode because 5 undoes 6. 5 is the multiplicative inverse. So 15 times 5, 75. 24 times 5 is 120. 135. 120. 0 times 5 is 0. 135, 0, 135. 26 times 5 would be 130. 20 times 5 is 100. 12 times 5 is 60. 24 times 5 is 120. Okay, so we multiplied by 5. That undoes multiplication by 6 because 5 and 6 are inverses. That's why we spent all that time and effort finding the multiplicative inverse. Now, take the results mod 29. Subtract 29 over and over till you get a number between 0 and 28. So 75 minus 29 minus 29, 17. 120 minus 29 minus 29. 9. Yep, 4. Okay, 135 be 19, I think. 75 we know was 17. 120 is 4. 0 is already small enough. We'll just leave it 0. 135 we know was 19 because we already did it. 0 is already small enough. 130 would be 24. 14? Yeah. Sorry. 14. 100. 13. 60. 2. And 120 was 4. Okay. Now change them to letters. R, E, T, R, E, A, T, A, T, O, N, C, E. Retreat at once. Okay, so now number 2 on your worksheet that I gave you is to find a multiplicative inverse and then use it to decode a message. Okay, so go ahead and do that now. Okay, so let's look at this together. They told you that this message was encoded by using an affine cipher that multiplied by 5, added 1, and then took the result mod 29. So to undo multiplication by 5 and then adding 1, first you need to subtract 1. Undo the plus 1 by subtracting 1, so we get 1, 11, 27, 0, 25, 25, 20. So that undoes the plus 1 part. To undo the multiplication by 5, what do you multiply by? 6, because we know that 5 and 6 are inverses in mod 29. So I'll take each of these numbers, multiply them by 6, and I get 6, 66, 162, 0, 140. Then I take these,
120.
the last one, thank you. Then I take each of these and take the mod 29. Okay. So 6 is already small enough. 8, 0,
5, 5, 4.
okay, and that decodes to G, I, R, A, F, F, E. Giraffe, yes.
In the last step before we make it to letters,
It would not be. Because we started with letters and we encoded them. So the decoding process is always going to get you back to where you started, and none of your letters would have been 27. Okay, so let's do one more for practice. Find the multiplicative inverse of 7 in mod 29 arithmetic. What do you multiply 7 by to make 1, or a number equivalent to 1, in mod 29? Okay, so we know that using prime numbers means it will always have a reversible cipher. Okay, so that's why we choose 29, because it's prime. Okay. But in general, finding the inverse operation can be difficult, right? Like this took a long time. We had to try a lot of numbers before we came up with the 25. So finding the inverse operation that undoes what you did is not always easy, particularly if your prime numbers are big, right? 29 is in the grand scheme of things, a baby prime number, right? It's a little bitty one. We can make prime numbers that are hundreds of digits long, that are really, really big prime numbers. That makes finding the inverse operation super difficult. Okay, so this is the basis of something called public key cryptography. Okay, Affine and multiplicative ciphers are asymmetric. That means that the method for decoding is not easy to figure out, even if you know how it was encoded, right? So even though you know it was encoded by multiplying by 5 and then adding 1, you have to do some work to figure out how to decode it. We had to do some work to figure out that, oh, we should subtract 1 and then multiply by 6. So asymmetric ciphers allow for a system that's called public key cryptography. And in a public key system, everyone has two keys. Everyone has a method they use to encode messages and a method they use to decode messages. So with a multiplicative cipher, the key would be the number you multiply by to encode and the number you multiply by to decode. Those would be your encoding and decoding keys, like the 5 and the 6. The difference in a public key system is that the encoding keys are public. Everybody knows the encoding keys, and it's all in like a public folder somewhere. So there's a big database, and it says like Caitlin Worth, encoding key 5, right? So if you want to send me a message, you encode it by multiplying by 5. But I'm the only one who knows that to decode it, you multiply by 6. Someone could figure it out with a little bit of effort, right? But if I use a really, really big prime number as my modulus, and I could say multiply by 5, figuring out what to multiply by to decode would be really hard. A computer could do it in a matter of years, right? It could work really hard for years and years and maybe finally come up with the decoding key. So we rely on the fact that people cannot figure out the decoding key in a timely way, in a way that makes the information still relevant. So for a system like this to work, it has to be really difficult to figure out the decoding keys from the encoding keys. So we did an example that was like a little bit difficult, but you all did it. Okay? With a public key system, it has to be really difficult. So this is how it works. Suppose Adam wants to send a message to Beth. So he encodes his message using Beth's public key. So only Beth knows how to decode the key that she puts out there. She says, if you want to send me something, encode it like this and send it to me, because only I know how to decode it. So anyone can send a private message to Beth like this, and only Beth can read them. So you can think of it like this. Using Beth's public key to encode a message is like putting the message in a special kind of box that only Beth can open. So let's say Beth's boxes are blue. Only Beth can open blue boxes. But anyone could go to the store and buy a blue box and use it to send to Beth. But once you seal it up, only Beth knows how to open it. And Adam's boxes are red. Anyone can go to the store and buy red Adam boxes, but only Adam can open them. So if Christine sends Adam a message using his public key, she doesn't have to worry about Beth intercepting the message, because only Adam can open red boxes. But anybody can buy them. So affine and multiplicative ciphers are actually substitution ciphers. They're susceptible to techniques like frequency analysis. So they're unsuitable for public key cryptography. I just wanted to show it to you because it gave an example of how it's difficult to figure out the decoding key. Okay. Public key cryptography is going to require a code that's virtually unbreakable because we use it for things like our credit card numbers on the internet, emails, national security messages. It has to be virtually unbreakable. The most common system we use today is the Rsa Code. It relies on the same ideas that we worked with today, prime numbers and inverse operations in modular arithmetic. And when prime numbers are really big, it's hard to find inverse operations. So the prime numbers we use for the Rsa Code are many digits long. So for example, this is a typical security message you might see in a web browser. High-grade encryption, 128-bit. That 128-bit means that the encryption key, the number you multiply all everything by to encode, could be as large as a 39-digit prime number. Really, really big prime number. So to figure out the multiplicative inverse of that really large prime number would take a really long time. Okay. Even with a computer checking 1 billion keys per second, it would take about 10,000 billion years to check them all. It's far, far longer than someone could reasonably have to break the code. It makes breaking the code take an impossibly long amount of time. And as computers get better and faster, we just make the encryption keys longer and longer. And there are an infinite number of prime numbers, so we can just keep picking bigger ones. And that is it. So Thursday will be a review class. I gave you the study guide. We'll discuss it then.